Let's start. So you're going to notice during this unit that it says Physics 11. If it makes you feel better, you can cross that out and put a 12 there. We're looking at a unit I didn't get to last year because of COVID, and it's a fundamentally important concept. So we're going to go very meticulously. The unit is looking at work and energy and power. And there's a bit of a problem because those three words, work, energy, and power, Grace, they have different English meanings than physics meanings. For example, in physics, work has a very, very specific meaning. When you say you're doing work, what you really mean is you're getting tired. Work is not tiredness. There is a physics concept that is tiredness, and we'll talk about that after the break. But in physics, work is not something that you do that makes you feel tired. Work is done on an object. You do work on an object. When you do work on an object, you've changed its energy state. If you do work on an object, two things must happen. A force must act on the object, which means all of our F equals what, winner minus, is still fair game. And the object must move through a distance in the same direction as the force. Underline that. That's going to be important. If an object is moving a distance, but it's not in the same direction as the force, no work is being done. Even though somebody's pushing on it, if it's not moving in the same direction as the force, no work is being done. Work is a scalar. That means no need to go tip to tail. And it's calculated by force times distance. Write that down. What would the units be? Oh, our symbol for work, capital W. And again, we're running out of letters because capital W is also West and capital W is also watts. But if it's on the left side of the equal sign, work. Well, what would the units be? What do I measure force in? What do I measure distance in? So it's a Newton meter, but this unit is so important, we've given it a name. We call a Newton meter a joule, symbol capital J. However, this equation only works if the force is constant. I opened class up with the rocket thought puzzle. In that rocket situation, because the mass was changing, the force, the force would be constant. It would still work there. Sorry, I take that back. If the force is changing, you can't use force times distance. In fact, we're going to learn today 3 different ways to calculate work. This is the easiest one when you have a nice clean situation, and then we'll ask, what if things get messier? Okay? Harsh, can you stand up, please? Can you walk behind Marcella, face the wall, and I'd like you to push against the wall as hard as you can. Push hard, push really hard. Come on, put your back into it, okay? If I asked Harsh to do that for an hour, would he get tired? Is he doing work? Is he applying a force? Yes. Is the wall moving any distance in the same direction as the force? So in physics, is he doing any work on the wall? No. Work is, you can sit down now, work is not tiredness. Okay? Is that right? Jack and Manchan, can you both stand up, please? Rock, paper, scissors, best of one, you want to win.
I win.
Okay? Jack, you played scissors, Manchan played paper, Manchan loses. Manchan, can you stand on this side of Jack, please? Jack, can you stand behind Manchan? Manchan, can you give Jack a piggyback, please? I know. Hop up. Jack, hop up. Okay, stop for a second. What direction is the force acting on Jack right now? Get the obvious one. Which way is gravity pointing? Walk forwards. Even though Mansion would be getting tired, because his distance is forwards, but he's resisting a gravitational force, is he doing any work on Jack? No. No work is being done because the force and the distance are not in the same direction. You can put him down. You can put him down now. I have to really drum this out of you because people tend to think, oh, I'm getting tired, I'm doing work. No, you're not. Not unless the force and the distance are in the same direction. So, how much work does it take to lift? Underline the word lift, please. A 12-kilogram mass from the ground to a height of 9.5 meters. Okay. Since we're doing a brand new topic and concept, we'll go back to our DFIC method, I think. What's this question asking me to find? How much what? Let's go. W equals question mark. We'll fall back onto familiar territory and be meticulous. What's our equation for work? The new one that we just learned today. Work equals what times what? Okay. All right. Over on the right in the margin, we're going to do a little free body diagram. Let's assume you're lifting it up at a constant speed. What are the forces acting on this object? Get the obvious one. Get the obvious one. Get the obvious one. Anybody, come on, loud and proud. What? Okay. If you're lifting it up at a constant speed, I'll call that, I don't know, F lift. How big is F lift compared to gravity? Bigger, smaller, or the same size if you're lifting it up at a constant speed? Okay, so let's draw an arrow pointing up. We'll call that F lift. And so I'm going to argue that this is F lift times distance. You okay with that? I don't know F lift. Oh, but look. I know another force that's exactly the same size as F lift, assuming I'm lifting at a constant speed. Which force is exactly the same size as F lift? Okay. The work done when you're lifting an object is given by mgh. And we go to h because it's a height and we're in Scalarville. It's not a displacement. You'll probably just memorize that when you're lifting something, the work is mgh. In fact, if you look at your formula sheet, you'll notice later on, we'll describe mgh as potential energy. And so you don't need to do this derivation again, but I'm just walking you through it once. Lifting, the work done by lifting something, gravity is not pointing in the same direction that you're lifting, but the force that you're exerting up has got to be the same size as gravity. Otherwise, you couldn't be lifting it up. You okay with that argument? Good. Marcella, what's M in this question? G. And we're in Scalarville, no negative. H. What do you get? $12 kilograms, about 30 pounds. So heavy, but not heavy. 9.5 meters, about 3 stories. So this would be like carrying a fairly heavy box up 3 flights of stairs. How many joules? 1,000. 1117? I'm going to label it as 1,120. I'll go to 3 sig figs. Basically, all of you are capable of putting out 1,000 joules of work. It would take a little oomph. You wouldn't want to keep doing this all day, but all of you are capable of carrying a fairly heavy box up 3 flights of stairs, moving furniture, you know, that kind of thing. Coal, can you cross out the word coal, please? Harsh. Pushes against a brick wall as hard as he can for 12 seconds. Amazingly, the wall does not move. How much work was Harsh doing? Was he getting tired? Yeah. Was he doing any work in our physics definition? No. Okay. Suppose you're pushing a box across the floor and it requires a steady force of 22.5 newtons. If you push it for 13.6 meters, how much work have you done? What's this question asking me to find? Well, work equals force times distance. Did they give me a force? Yeah. Now, by the way, could I have given you instead enough information to find the force by using a free body diagram? Who's winning, who's losing, equal MA? Yes, I don't think I'm going to do that for a while because we've just done a unit on forces. But you can certainly take all of the stuff we just finished and work it into here. So, Jack, did they give me a force? You already answered. How big? And it's a steady force, not a changing force, because this equation only works for a constant force. Did they give me a distance? Are the force and the distance in the same direction? Imagine the situation. Are the force and the distance pointing in the same direction? Then I can use this equation. What do you get? You get 306 joules. Okay. Now, here's what else that means. You can also measure energy in joules. What this means is your body gave up 306 joules of food energy in order to do 306 joules of work pushing that object. Okay? And if you did that for a long time, you would feel tired, not because work is tiredness, but because your body is contributing calories to this object in order to move it. I'm being really careful in my terminology here. Dylan pedals his bike up a 19-meter high hill that is 91.4 meters long. The combined mass of bike and rider is 65 kilograms. The bike requires a steady force to continue up the hill. First question. Suppose Dylan used a rope to climb vertically up the backside of the hill. How much work will this require? Pause for 1 second. Our first question, part A. Suppose instead of riding the bike up the hill, slanty, at an angle of 12 degrees, Dylan just climbed the back of the hill on a rope. How much work would this require? Well, Davis, work is what times what? What was the force if you were lifting an object? We did that free body diagram and we made the argument that the lifting force is the same size as which force? So, you know what? The work is going to be mgh. Okay? What's m, Davis? G, H, 19, okay? This is how much work it would take to climb the back of the hill carrying the bike with you if there was like a ladder that you could climb or a rope that you could climb. How many joules of work will it take Dylan to carry his bike straight up the hill vertically? Davis, what'd you get? 12,103 joules. Is that right? Yep. Okay. Here is why work and energy, stay here. Here is why work and energy are so nice. B says, how much work will Dylan do riding his bike up the hill the long way? The answer is because work is a scalar. When he's riding up the hill, which force is he doing work against? Gravity. So if you, now, we all have enough skill. We could have also done this. We could have said gravity component, we could have said mg parallel is the force that he's going to have to do work against, and we could have used this 91.4. And if you run the numbers, if you go work equals mg parallel, well, you know what? mg parallel, mg 2 lines is what? If you go m 65, g 9.8, 2 lines is sine 12, close bracket, good morning, times 91.5, 91.4, same answer. Minus some rounding, same answer. And so the reason that work and energy are so convenient is if you have a yucky path and you don't want to deal with the yucky path, and you can say, I can do the same amount of force times distance in a different path, you'll get the same answer. Okay? Let me pause for a second. If we had done this in Physics 11, I couldn't have told them mg parallel, mg 2 lines. They wouldn't have known any of that. But what I would have said to them is, because work is a scalar, in fact, look up. If the hill did this and still reached a height of 19 meters, I could then say the amount of work to pedal this would be mgh. I don't care about the path it took to get there. And so I use work and energy anytime if there's a change in height and a change in speed and a yucky curvy path. I will not use, Emma, a vector-based approach that would require me to calculate every single angle along the way. Calculus would let me do it. I would still run away from that. I would use a scalar approach anytime I could. So C says, using your answer from A, calculate what force that Dylan needs to pedal with in part B. Work equals what times what? Work equals what times what? So if I go work equals force times distance, if I want to calculate the distance along the hill, so if I use the distance along the hill, that will help me figure out the force along the hill. In other words, how would I get the F by itself here, Kyle? It turns out another definition for force is the amount of work divided by the distance that's in the same direction as the force. So since this question wants me to find the force up the hill, to pedal up the hill, I can use the work, my answer from A, and I can divide it by 91.4. So my answer from A was 65 times 9.8 times 19. There was the 12,103. If I divide it by 19.4, that's the force required to pedal up the hill. And in grade 12, I can say to you, if I go mg sine, I don't know, because I made a big typo. Thank you. 12,103, and it spoiled my punchline. If I divided it by 19, not 19.4, Mr. Dewick. Sorry. I want to divide it by 91.4, not 19.4. There's the force up the hill, and you can see they're almost bang on. I rounded off a tiny bit, because if you do the trig, if this is 19, this isn't exactly 91.4, it's 91.38, something. So what did we get for our force? 132 newtons. The long point of that is this. If you have a certain amount of work to do, you can either use a big force over a short distance, or you can do a smaller force over a big distance. If I have to climb a hill, better yet, if I have to climb a house, if I need to get to the roof of a house, I can go the shortest distance straight up a ladder. That will require the biggest force. I'll be competing against mg. Or if I have a big ramp that leads to the top of the house, I can go nice and slowly. We do this all the time with stairs. Stairs, basically, instead of having you have to climb a ladder to get upstairs, which would be the maximum amount of force required but minimum amount of distance, a stair increases the distance but reduces the force, so much so that you can do it casually without thinking about it. You're still doing the same amount of work. So this is one of the nice characteristics, next page, about work. It's a scalar. How much work would it take for Dylan to ride to the top of this hill? Still 12,103 joules. No difference. Heck, even if the path did this, dropped down below the ground and came back up, doesn't matter. You're still doing 12,103 joules of work. What this means, Owen, is we can start to analyze roller coasters, and we will after spring break. What takes more work? Lifting a 25 kilogram mass to a height of 4 meters, or lifting a 50 kilogram sack to a height of 2 meters? What takes more work? What? They're the same. And you could go MGH, but you know what? Lifting half the mass, twice the height, would be the same as lifting twice the mass, half the height. Okay? Work equals what times what, Harsh? That only works if the force is constant. What if the force is not constant? What if it's changing? Here is your second definition of work, not as clean as force times distance. Work is also the area under a force versus displacement graph. I like example 7. I like example 7. Example 7 is a nice question. Grace, what's example 7 wanting me to find? Keep reading. 2 meters is right here. 5 meters is right here. Do you notice, Grace, the force is changing because it started out there and it ended up there. I can't go force times distance. I can't go 3 meters is the distance, 8 newtons is the force. 8 times 3 is not 24. So, did they give me a graph? I'm probably going to find the area underneath the graph. So can all of you go like this? Okay. Don't write this next bit down. We need to find that area there. Don't color that in yet, though. What shape is that? What do you call 2 parallel sides and 2 non-parallel sides? It starts with the letter T. Not a triangle. TR. This is a trapezoid. Anybody know the formula for the area of a trapezoid? There is one, and I always ask because every once in a while I have a math nerd who has looked it up. There is one. We don't bother teaching it because it's redundant. Any trapezoid anywhere can always be broken up into, draw this, a rectangle and a triangle. I've never yet been able to draw a trapezoid that I couldn't break into a rectangle and a triangle. Have you been taught the formula for the area of a rectangle? Yes. Have you been taught the formula for the area of a triangle? Yes. Now the formula for the area of a triangle, I think I also put on your formula sheet on that back page where I have some trig stuff, but I do expect you to know the area of a rectangle. So we want that whole area. Do me a favor, let's call this bottom one, let's label it with a number 1. Let's label this top one with a number 2. Grace, what was this question asking me to find? How much what? Why can't I go force times distance? Because the force is not, I'm looking for a word that starts with the letter C. Not a constant force. So, this is your checklist. Whenever it says how much work, force times, oh, can't use that, they gave me a graph. So, work is going to be this area. The area of shape 1, well, what is shape 1? Sesame Street is brought to you today by a rectangle. What's the area for a rectangle? What's the length? 3. 5 minus 2. What's the width? 6? No, 2. 2? Yes? In your head? 6. Now, let's find the area of the second shape. Percy, what shape is that second shape? What's the area of a triangle? It's on your sheet if you don't know it. You want a clever way to remember it? Any triangle is always half a rectangle. But usually instead of writing length times width, we write base times height. But any triangle, look, it's half a rectangle. Clue in. But I think I put half the base times the height, or base times height divided by 2, or 0.5 base times, something like that, yes? So, Percy, how long is the base of this triangle? Yep. What's the height of this triangle? You have to figure it out from the graph. Yeah, you have to do a little thinking. Divided by 2. In your head, 3 times 6 divided by 2. Yeah. How much work? In your head. No, not times. We're finding the total area here. We would add them, right? This has an area of 6. This has an area of 9. What's the total area? Okay. So, work is force times distance. Work is also the area underneath a force versus displacement graph. Paige, when do I use that second one? When they give me a force versus displacement graph. It's pretty obvious. So we now have 2 definitions for work. Force times distance, but this requires a constant force, and the force and the distance have to be in the same direction. Or, work is the area under a force versus displacement graph. Calculus students, you didn't get to integration this year, but the opposite of a derivative is called an integral, and that's an area. So, hugely useful. Example 8. How much work was done moving this mystery object 10 meters? Can I go 30 times 10? Why not? Clearly a changing force. So it's going to be this area. How will I break it up? I think I'll break it up into this triangle and this rectangle. Good. Find it on your own. I'll do it up here. Let's see if we get the same answer. Yeah. First one is a triangle, base times height divided by 2, 10 times 10 over 2. Hey, I can do that one in my head, 50. Second one is a rectangle, base times height or length times width, 10 times 20. I can do that one in my head, 200. So 250 joules of work. So if you were pushing this object 10 meters, your body would have lost 250 joules of calorie energy, food energy, and that would have gone into this object. How would that have changed the object? We haven't talked about that yet. But step 1, work involves an energy transfer. You do work on an object. It's not getting tired. Example 9, 124 kilogram box is being pushed along a floor that has a coefficient of friction of 0.25. I'm already suspecting a free body diagram in our future just by reading that. The person pushing applies a force of 525 newtons over a distance of 22 meters. Okay. Cool. Kai, what's A want me to find? Work done by person. So I'm going to go, how about work person? I guess that's going to be force person times distance. Well, what's the force that this person is pushing with? What's the distance? Reading this question, does it look like the force and the distance are in the same direction? I think so. How many joules of work did this person do? Okay. 11550, and we're going to carry all the extra sig figs because we're going to use this. B. How much work is done in overcoming friction? I think this is asking me to find the work that friction did. Well, if the work that the person did is the force of the person times distance, what do you think the work done by friction was? The force of what times distance? Yeah. Well, free body diagram. We have mg, normal force. We have F applied. This is 525 newtons. Friction. Okay. Armand, friction is what times what?
Mu times the normal force, Mr. Dewick.
Oh, Armand, you are ever so clever. Yeah, but I'm hoping he's watching on YouTube and I gave him a shout out, right? I know he's waiting it. Wait a minute, I don't know the normal force. Oh, but look. I don't know the force the same size as a normal force. What? Yep. Times distance. So, wait a minute. Well, work equals 0.25 times 124 times 9.8. I've got a bit of a problem here. Which way is the distance to the right? Which way is friction pointing? Left. They're not in the same direction, but they are in the same plane, in the same frame of reference. How could I show that we're pushing in the opposite direction of the distance? What do you get? You get negative 6,683.6. Now that negative, remember, work and energy are a scalar. That negative actually isn't saying backwards. It's saying you lost that much energy to friction. It's a value. It's a measurement. It's how much. We lost 6,683.6 joules to friction. How much energy did we put in? 11,550, but only some of it went into pushing the object. 6,683.6 went into just overcoming friction. In fact, it went into heating up the floor. The same way when you rub your hand hard against our lab tables, you can feel that you're generating some heat. That energy got lost as heat. So if you ask me what the network done on the box is, the network is going to be 11,550, but we lost 6,683.6. What was left over to push on the box? 4,866.4 joules. Where did that energy go? That's the energy that went into making the box accelerate, speed up. But a lot of the energy went into overcoming friction. A lot of the work went into overcoming friction. What's your homework? Number 1, 2, 3 is good. You can skip 4. 5 is good. 6 is good. 7 is good. 8 is good. Every time you say skip something, I'm probably going to do it. Nice try. I say yeah, 9. 10 is good. So yeah, I gave you all of it and the take-home quiz, but now I'm going to press pause. So the rest of the class is yours to work on the homework.